Welcome to the PyTorch Summer Hackathon 2020. I'm Brad Heintz, and I'm a partner engineer with the PyTorch team. If you're not sure what a partner engineer is, it's my day job to make sure that developers like you get the absolute most they can out of PyTorch and related tools. In this video, I'm going to show you how to deploy your machine learning model with TorchServe. A trained machine learning model alone does not make a full-fledged application. You'll need to integrate it into a larger system. In this video, I'll be using the term model serving to refer to this integration and subsequent use of the model. Recently, the PyTorch team released TorchServe, which is the preferred model serving solution for PyTorch. It's a performant and scalable tool for wrapping your PyTorch model in an HTTP or HTTPS API. In this short video, I won't be going into the advanced features of TorchServe. Instead, I'll be focusing on the stuff you'll need for a hackathon, namely how to stand up your first TorchServe installation and start serving inferences from your model. In this video, I'll be showing you how to package your model and any supporting files it needs in a model archive and place it in the model store where TorchServe can see it. How to apply the default model handlers that TorchServe provides for certain use cases, and how to create a custom model handler if you need one for a new use case. Starting TorchServe and configuring it for serving your model via TorchServe's Inference API, examining and manipulating server state with the Management API, and where to go to find log files so you can see what's happening under the hood. For this walkthrough, I'm going to show you how to set up a simple image classifier in TorchServe. Everything I'm about to show you is documented more thoroughly at pytorch.org/docs and at github.com/pytorch/serve. First, make sure you're in an environment with PyTorch 1.5 or higher. You'll also need OpenJDK 11. That's version 11 of the Java Development Kit. Next, install TorchServe and the TorchServe Model Archiver. You can use pip or Anaconda for this. I'll be using Anaconda. When installing with Anaconda, don't forget to use the PyTorch channel. That's -c PyTorch on the command line. Now, I'll show you some optional steps to optimize your model for use with TorchServe. They aren't strictly necessary, but will often improve performance and memory footprint, so I encourage you to try them and profile the results with your own model. So, first things first, we'll import PyTorch and TorchVision. And this is a good place to point out that you should be using PyTorch 1.5 or higher for this example. In the next cell, we're going to create a PyTorch model object. Now for the actual app, I have a pre-trained optimized model ready to go. But for the optimization process, I wanted to show you this on a custom model so that you could duplicate the process with your own models. This model happens to contain some very common layer types, a 2D convolutional layer, a 2D batch norming layer, and a rectified linear unit for activation. And the forward function just strings those three operations together. So now that we have our model, how do we optimize it? First thing, let's get an instance of the model. In my get model helper, you'll notice that besides just instantiating the model, I call m.eval. So eval turns off things in the model that you don't want on during inference time. Training only layers like dropout, automated gradient tracking. All this training related stuff eats up CPU cycles and we don't need it for inference. So we're going to make sure the model's in eval mode. The second thing we're going to do is some layer fusion. Fusing layers means taking multiple operations and combining them together into a single operation. This improves performance and memory footprint. Now, with the fuse modules method that I'm going to show you, there are only certain combinations of layers that you can fuse together. I'm going to refer you to the documentation for the latest information on that, but here we're going to try to fuse together a convolution, batch norm, and a ReLU. Once modules are fused, the next thing we're going to do is quantize the model. PyTorch tensors default to using 32-bit floating point numbers as their underlying type. When we quantize, we're going to change that to an 8-bit integer. This will perform faster and reduce the model's footprint both on disk and in memory. The final thing we're going to do is save the model as TorchScript. TorchScript is an optimized format for your model, including both your computation graph and your learning weights. It's meant to be consumed by the PyTorch just-in-time compiler, or JIT. So once it's exported, we'll save. Now, there are subtleties to layer fusion and to quantizing your model that you'll want to be familiar with when you're optimizing your own model. All of this is covered in the PyTorch documentation for quantization, which I encourage you to check out. Once you have your model ready, you'll need to create a model archive and place it in the model store. The model store is just a folder that holds your model archives. A model archive is a single file bundle that includes your model and any supporting files you need. For a natural language model, that might be a vocabulary or an embedding, or if you're deploying a non-TorchScript model, you'll also need to add the Python file that defines your model class. So let's make the model store, and we'll create a model archive for our model. I'll be using my own model with the learning weights saved in a .pt file and the model code in the .py file. I'm also going to pull down a single file from the TorchServe GitHub repo. It's just a JSON file that has all of the human-readable labels for the categories my model is trained against. Let's take these 3 files and make a model archive out of them. The important things I'm specifying on this command line are: I specify the name of my model endpoint with the model name flag, the version of the model. TorchServe can simultaneously serve multiple versions of the same model for things like benchmarking and A/B testing. With the serialized file flag, we specify the file that contains our model's learning weights. The model file flag specifies the Python file that contains your model's class definition. The model handler flag lets you specify code that pre-processes and post-processes data for your model. Here, I'm using the default image classifier model handler, but if I were using a custom handler, I'd specify a path to a Python file with the model handling code. For more details, see the PyTorch documentation and the GitHub repo for TorchServe at github.com/pytorch/serve. And finally, the extra files flag lets you specify a list of files to include in your model archive. Here, I've included the index that contains the human-readable names of my categories. So let's look at what we have and recap briefly. We have created the model store folder, gathered the files we need, a model, its Python file, and a supporting file with the human-readable labels for our categories. And finally, we combined these files into a model archive file. The final preparatory step is to move the model to the model store. Now we have everything we need to start TorchServe and serve our model. This is how we'll start TorchServe. The important arguments here are the start flag, because we're starting TorchServe. The NCS flag stands for No Configuration Snapshots. By default, TorchServe stays its state and will restore it the next time you restart it. To avoid confusion for your first time using TorchServe, I've turned that feature off. We specify the model store because that's where our model archives are. And finally, with the models flag, we can specify a list of model archives that we'd like to serve. You must specify the model archive file name. The piece to the left of the equal sign is the name of the API endpoint and is optional. So now I'll actually start TorchServe, and you can see a lot of log info scrolling by. Worker threads are being started. Models are being loaded into memory in those worker threads. So just for the sake of tidiness, I'm going to flip over to another terminal window. If you want to check the status of TorchServe and your endpoint, you can use the Management API. This call tells us which models we're serving. If we want to drill down on detail for a particular model, we can specify it in the URL. And now we can see that we have 4 separate worker threads, all serving version 1.0 of my CV model. You can also use the Management API for adding and removing models and model versions and changing the number of worker threads assigned to a model. All of this is documented in the docs at pytorch.org and with example code at github.com/pytorch/serve. So let's do some actual inference. I happen to have an image file ready, and so let's see what my model thinks this is. For that, we'll use the Inference API. On this command line, we're going to specify our server and port. By default, TorchServe uses port 8080. We're going to call the predictions endpoint, and we're going to specify which model we want to serve the prediction and the path to a file for input. And sure enough, my model thinks the picture of a cat is a picture of a cat, so that's success. The last thing I need to show you is how to stop TorchServe. You just call TorchServe from the command line with the stop flag. And that is TorchServe in a nutshell. And there's a lot more to learn about TorchServe, multiple methods for configuration, configuration snapshots for setup convenience, and custom handlers for new use cases. Again, I strongly recommend the documentation at pytorch.org/docs and the examples at github.com/pytorch/serve. Thank you for watching and for participating in the PyTorch Summer Hackathon 2020.